Hello friends, in this video we will discuss a small topic of NMR spectroscopy, that is anisotropic effect. Before going into this anisotropic effect, there are some basic understanding you must first know that is necessary, and I will just give you some glimpses of that. First thing is you must know about chemical shift. What is a chemical shift all about? It is nothing but number of signals that is signals of sets of equivalent proton, and this position of signal describes the nature of the respective proton. That means whether it is aromatic, aliphatic, acetylenic, vinylic, adjacent, or it may also explain the environment of the adjacent protons, whether it is attached to an electron withdrawing or electron donating groups. And uh, when the compound is applied to a magnetic field, and under this external magnetic field the electrons circulate, and due to which they generate a secondary magnetic field, which is commonly known as induced magnetic field. And basically this induced magnetic field there are two categories. It may oppose the applied magnetic field, or it may reinforce, or it may favor the applied magnetic field. Now if it opposes the applied magnetic field, that means it is opposite. Induced magnetic field is opposite to the applied magnetic field. The the actual if field effective field felt by the proton is diminished. It will be diminished, and the proton is uh, thus said to be shielded protons. That means when it opposes, it is called a shielding effect, and when the induced magnetic field reinforces or favors the applied magnetic field, such effect is called deshielding effect. And based on this shielding and deshielding, there will be the specific chemical shift. It have a specific effect on the delta value of a particular proton. So this may be the some small understanding, and which we may cover in our some of our videos. uh, Talking to our main effect, that is anisotropic effect. This is nothing but it is a space effect. Let us take an example of an ethylenic proton. There is a deshielding effect on the proton which are attached to the carbon-carbon double bond, and thus they have comparatively higher delta value than the protons attached to carbon-carbon single bond. Here, let us take an example of an ethylenic proton, that is an alkane. Here, it is so oriented that the plane of the double bond is to the right angle to the applied magnetic field, applied field. And the induced circulation of pi electrons thus generates the induced magnetic field, and this magnetic field, induced magnetic field, is in this direction from inside to outside. It is constantly uh, in this direction. So what happens uh, when this field is in this direction? Here, considering this portion, this portion, this induced magnetic field opposes the applied magnetic field. That means here it is diamagnetic, and here where the protons lie, here it reinforces. That means it favors the applied magnetic field. That means here it is paramagnetic to the applied magnetic field. Thus, due to this effect, the induced circulation generates the field, and generates a field in such a way that the proton will feel the greater field strength, and hence the resonance will be applied at the lower applied field. So these induced magnetic field of this proton, for this proton, it favors the uh, applied magnetic field. That is why they are called paramagnetic, and they appear at a lower applied field. That means their delta value will be comparatively higher. Let us try to understand by our next example, that is an alkyne. Here the electronic circulation around a triple bond takes place in such a way that the protons will experience the diamagnetic shielding effect. Here the shielding effect, the secondary induced field is in this direction from inside to outside. So the applied magnetic field here is this. So the protons of the alkenes are diamagnetic. That means they have the effect which is opposing to applied magnetic field. Thus the proton, this proton will feel a smaller field strength. That means they are shielded, and hence resonance will occur at higher applied field. That means they have a respectively low delta value. That these protons are said to be shielded, and the example we saw earlier, these protons will be said to be deshielded because it favors the applied magnetic field. So this is the basic difference between a shielding and deshielding. Let us look around our next example, that is a benzene. In case of benzene, the loops of pi electrons are delocalized cylindrically over the aromatic ring system, and these loops are they produce an induced, and they circulate in presence of the applied magnetic field. This is the applied magnetic field, these are the pi electrons, and this induced current is diamagnetic inside the ring and paramagnetic outside the ring. The induced field generated by these electrons is in this direction, in this position. As I said, it opposites to the center and favors opposites the induced magnetic field, and it favors, here it favors where the protons are lying, it is favoring to the applied magnetic field. Hence these protons will experience a magnetic field comparatively greater magnitude than the applied magnetic field, because this field, this induced field, is adding up with the applied magnetic field. So effective field for this proton will be greater than the that is applied, because induced magnetic field, as I said, induced magnetic field here is favoring the applied magnetic field. That means these protons are paramagnetic outside the ring. Such protons will be, as I said again, called as deshielded protons, and hence they will need a very lesser amount of applied field. That means they will have a higher delta value to bring them to the resonance. Is nothing, we are talking about the flipping of proton. That is once again a concept of one of the concept of NMR. So this is an example 18 annulin, which is a very good example of shielding and deshielding by the ring currents. As I said, in benzene ring, the protons are deshielded. That means they have a higher delta value. Here, same way, there are two types of proton. The induced magnetic field is in this direction. It moves from this direction, and it favors the protons which are lying outside the plane, but it opposes with the protons which are lying inside the rings. That means in 18 annuli, these protons are said to be shielded protons, and the protons which are lying outside the ring, that means these protons will be said to be deshielded, because the protons which are circulated by the black color will favor the applied magnetic field, and the protons which are shown by this blue color, the red color, will oppose due to oppose the applied magnetic field. So these protons which are lying inside the annulene are said to be shielded protons, and the protons which are lying outside the ring are strongly deshielded protons. So this is the very best example of the shielding and deshielding. This was all about anisotropy. Anisotropy once again is nothing but a uh, effect that can be explained in by a space effect. Space effect. Hope you will understand the topic, and this will be very helpful for your future. I will come up with more videos and more crisp and precise explanation. Thank you for now.